This is problem 8 in the text in section 2.1, Pennies on a Checkerboard. You have a choice. Take $1 million or take pennies on a checkerboard placed as follows. On the first square, place 1 penny. Then on the next square, twice as many as before, thus placing 2 pennies. And on each subsequent square, placing twice as many pennies as in the previous square. There are 64 squares on a checkerboard. What is your choice and why? Most students would choose, in fact, not just students, most people would choose $1 million immediately because they're only putting pennies on the checkerboard. But we're going to calculate how much money would be on the board and see if choosing the $1 million is a wise choice. Before we look at the board itself and try to figure out the answer to this question, you should write this down on a piece of paper and put it out to the side, because this will make the problem much easier, is to learn what doubling means. Each time we double the amount of pennies on the previous square. So we start out with 1, and then we have 2, and then we have 4, but consider 4 2 squared. And then we double 4 and we have 8, but notice we're just multiplying 4 by 2. In other words, we're multiplying 2 squared by 2. That's 2 squared times 1 more 2 gives us 2 cubed, 3 factors of 2. A factor is something that divides into the number, or it is part of a product, a factor. So when I say put 1 more factor of 2, I mean multiply by 2. The next we double, we know we get 16, but that is 2 cubed, 8 times 2, so we now have 2 to the 4th. 2 times 2 times 2 times 2, 4 factors of 2. 32 is 2 to the 5th power. 2 is the base, and 5 is called the exponent. Words are really important in mathematics because I'll use them all the time in lecture, and you need to know what they mean in order for me to communicate to you. So let's see, the next one, well, we could keep doubling easy enough, 64, but let's write it as 2 to the 6th. And I'd like you to have a list of these next to you. So if we double 64, we have 128, and that's equal to 2 to the 7th. And then doubling that, we have 8 and 8 is 16. 256 is equal to 2 times 2 to the 7th is 2 to the 8th. The next power of 2 will be 2 to the 9th. So we have to double 256. And what do we get? 2 times 6 is 12, 10, 11, 512. 2 to the 10th. We're collecting here, we're writing a list of powers of 2. So that would be 1024. And let's do one more. If we double this, we get 2048. 2048 is 2 to the 11th power. Now, just to make sure, words are very important. We are collecting powers of 2. We are looking at expressions 2 to the n. In other words, 2 times 2 times 2 and so on times 2, n factors of 2. So I'll turn this. This is n, whoops, where's my, okay, n factors of 2. A factor is part of a product. So 2 is a factor n times. And we call, change colors again, we call in this expression 2 is the base, and n is called the exponent. So again, make this little list on a piece of paper and hold it out next to you as we do the problem. Okay, so here is the checkerboard, and let's start. Notice it is 8 squares by 8 squares, so that's where you get the 8 squared is equal to 64 total number of squares, 8 by 8. Okay, so I'm going to start filling in. Where is my... Let's start filling in the amount on each square. We put 1 penny here. Here, let me go to white. We put 1 penny, and then we double it to 2 pennies. We double that to 4, and let's write 2 cubed instead of 8. And then multiply that by 2. 2 to the 4th we know is 16. 2 to the 5th is 32. 2 to the 6th is 64. And 2 to the 7th is 128. Also, maybe here I'll write in 128. Doesn't matter, but we can keep track of how many. Now, 2 to the 8th, 2 to the 9th, 2 to the 10th. But at some point here you think, well, do I really need to write in all of these numbers? 2 to the 10th is 1024, and by the time we get about over here, maybe to the 10th, not 10th, but maybe 11, 12, maybe the 14th box or so, the numbers are too big to write in the squares. So let's just see if we can generalize, find a pattern. Something I didn't tell you is that 1 is by definition called 2 to the 0. 1 is equal to any number to the 0. It's equal to 3 to the 0. It's equal to 5 to the 0. And 2, of course, is 2 to the 1. And 4 is 2 squared, 2 cubed, 2 to the 4th. So we notice that on the 8th box we have 2 to the 7th. This is the 8th box. 9, 10. On the 11th box here we have 2 to the 10th. On the 12th box we'll have 2 to the 11th. On the 13th square we'll have 2 to the 12th. So if we go all the way down here to the 64th square, how much will be on it? 2 to the what power? Well, notice on the 13th box we had 2 to the 12th. So this will be 2 to the 63rd power. So that's just what's on the last box there, and let's calculate how big that number is. Now I'm going to use my calculator to do this, and I'll tell you very slowly how I do it. Now in your calculator it might be slightly different. So I'm going to tell you the keys I'm pressing here, just so that you can figure it out on your own calculator. I'll use a different color. Okay, so this is how I calculate 2 to the 63rd on a calculator. Okay, so first I push 2 on my calculator. It might be different. First I push the key 2, and then I push the key that has this on it, y to the x power. Y to the x. I push that, and then I put in the exponent, 63. That's the next key. So this is telling me the base is 2, the y, press y to the x and 63, and then I will press equals. So that will give me my answer. And here's what I get. This is what my calculator gives me. 9.22337237, and then I have an x, which means times in this case, and I have a 10, and then above the 10 I have 0, 1, 8. That's what I see. A lot of you on your calculators, I've noticed most calculators don't give it to you that directly. They will give you the same number. They'll give you this. Now, possibly they'll only give you 9.22337, depending on how many digits you have on your calculator window, how many digits to the right of the decimal point. But you may have this exact same number, and instead of this notation here, you'll see a capital E, and then you'll just see 18. Well, that means times 10 to the 18th power. This here means this number times 10 to the 18th power. So when you multiply a number times 10 to the 18th, that means that you move the decimal point 18 places to the right. So let's actually write out this number. 9, and now I'm going to move the decimal point 18 places to the right. So I'll have 2, 2, 3, 3, 7, 2, 0, 3, 7. That's 9 places, 9 digits to the right. So I have 9 more to go, and that will give me 0, 0, 0, 0, 0, 0, 0, 0, 0. That's what I got in my calculator. Well, that's an awful big number, so I'm going to start over on the right and put in my commas so that I can read it. Okay, so let's see, hundreds, thousands, millions, billions, trillions. Did I do this right? Let's look again. Let's count the decimal. The decimal point was right here. Did I go 18 places? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Yep, we did. So this is like 9 quintillion pennies, though. So these are still pennies. So this is the number of pennies on the board. So how many dollars? Well, to change pennies into dollars, of course, we divide by 100. So when you divide by a power of 10, dividing by 10 squared, we move the decimal point to the left 2 places. So we're going to move the decimal point right here to get dollars. So I'll write the answer here in green. 9223 372 037 000 That's the number of dollars. And let's go ahead and put the commas back in so we can try to read the number. So this is 92 quadrillion dollars. Well, I have no idea. I haven't even heard the government talking of a number that big. So, and that's just on the last square. This amount of money is simply the amount on the last square. So do we have to even calculate any other amounts on the squares to know that this is certainly a better choice than $1 million? Well, of course not. So we'll choose the money, but what I want to do here is 2 things more. I want to find out the total on the board because the question asked us to, and I want to interpret this amount of money to see, to have it make sense to us. But before we do that, we're going to calculate the total amount of money on the board. To calculate the total amount on the board, well, you know what we would have to do. We would add up the amount in each of the 64 boxes. So that is a huge task. We cannot put all those huge numbers. We can't even put them in our calculators after a few squares because they have more digits than our calculator can handle. And so the calculator starts rounding off. So we can't use that method. We've got to find a pattern. So here's what we do. Let's say I go back to white. On the first box we have 1 penny. Now I want to write how much do we have on the first 2 squares. Well, we would add up 1 penny plus 2 pennies is 3 pennies. Now let's find out how much we have on the first 3 squares. Well, then we would add up 1 plus 2 plus 2 squared is equal to 3 plus 4, or 7. Just add up. How many are on the first 4 squares? Well, that's going to be the amount that was on the first 3 squares, 7, and we're going to add 2 cubed to that, which is 8, and we get 15. How about the first 5 squares? Well, we're going to take what was on the first 4 squares, 15, and add how much is on the 5th square. Well, that's 2 to the 4th, 16, and we get 31. Now, if you have that page next to you that had the powers of 2 on it, you might notice something here. Look at these numbers, 3, 7, 15, 31. And look at your numbers that you have written down. See if you see a pattern. When I ask you to do something like that, put the video on pause and see if you can see it yourself. In case you haven't, let's write how much is on the first 6 squares. Well, on the first 6 squares, 31 is on the first 5 squares, so we will add 2 to the 6th to that, or 64. And adding those together, what do we, wait a minute, on the first 6, so we have 1, 2, 3, 4, 5, 6, excuse me, that's 32 I should have added. Sorry about that. So 31 plus 32 will give me 63. Let's do one more. The first 7 squares. We have 63 plus, well, the amount on the 7th square is 64. So adding, we have 127. So do you notice something here? You could even notice it looking up at these values along the first row. Here we get the sum on the first 2 squares. Oh, I'm going to choose a different color, yellow. The sum on the first 2 squares is 3, which is, now put it on pause, you should get this yourself, it's equal to 2 squared minus 1. 7, look, 7 is equal to 2 cubed minus 1 on the 3rd square. On the first 4 squares, the sum of all of them on the first 4 squares, we get 15, which you see is 2 to the 4th minus 1. 31 is 2 to the 5th minus 1. 63 is 2 to the 6th minus 1. And 127 is 128 minus 1, which is 2 to the 7th minus 1. So on the 7th box, we have 2 to the not on the 7th box, excuse me. The sum of the first 7 boxes in this entire row here, the sum of the first 7 amounts of numbers of pennies, we have 2 to the 7th minus 1 pennies. So you can see a pattern here. We could say then, we can generalize right now. The pattern, it will give us the sum of pennies on the first 64 boxes or squares. In other words, the sum of all the money on the board. The sum of the first 64 squares will be 2 to the 64th minus 1. That's the answer to this question. but we want to change it into something that makes sense to us. So we have to calculate the dollars represented here, and then I'll try to make sense out of it by just Googling and seeing, is there anything that big? Is maybe the total amount of money in the world? I don't know. We'll check and see. So I'm going to do this on my calculator and show you what we get. First I clear my calculator so it says 0, and now I'm going to push 2 and then that key y to the x, and then 64 equals, and subtract 1, minus 1 equals. So here is the number that I get in my calculator, and you will get the same thing, maybe a few less digits to the right of the decimal point, or maybe a few more. But I get this number, 1.844674407 times 10, and then above it is 019. So that means times 10 to the 19th. So in order to look at this number, I'm going to move it 19 places to the right. But that will give me pennies. So let's move it 17 places to the right. In other words, we will have divided it by 100. So in dollars, I will have 1,844,674,407. That's 9 places to the right. 10, 11, 12, 13, 14, 15, 16, 17. I'm moving it, it's the same thing as moving it 19 to the right and then dividing it by 100 to get dollars. So now let's put in our commas and see if we can even read the number. Hundreds, thousands, millions, billions, trillions, quadrillions. So it's 184 quadrillion dollars. Now the zeros, we have to put zeros there because we don't really have this number exactly. The calculator can't calculate it. So what I can say is approximately. I'm trying to figure out how big this number is and comparing it to something that I'm used to listening to. And here is the United States national debt clock. So let's see, we have hundreds, thousands, millions, billions, trillions. Oh, well, it's much bigger than the U.S. national debt, so I'll try something else. So I Googled U.S. gross national product, or GDP. And this is very discouraging news. You see here that in most recent, this is 2013, we have $16,067.4 billion. Okay, well, so just for the heck of it, watch how we'd figure out what that is. I'll write it right here. We have, whoops, maybe I can't. Well, this is, you can do it on your own. That's about 16 trillion. So the bad news is that number is no bigger than our national debt. In fact, our national debt is bigger than our gross national product, the value of everything that we make in the United States in 1 year. Also, I tried something else. I Googled how much U.S. currency is in circulation. Sorry, I know that you can't read this. I don't know how to move the screen to the right, but we see here that there was approximately 1.23 trillion in circulation as of January 29, 2014. So what's on our board is more money than exists in U.S. currency. So I'm going to try one more thing. I'm going to Google how much money is there in the world, and let's see if 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 that's more than what's on the checkerboard. Here's what I got when I Googled how much money is there in the world. And of course, they're taking all foreign currency and converting it into its dollar equivalent. And it is the closest match currently available is about 58.9 trillion. Wow. 58.9 trillion right here. So we're going to write that number down. I'm going to go back to the checkerboard and we'll write that number down and compare it to how much money was on the 64 squares in total. This was the amount of money we calculated to be on the board, and what we just saw on that page was that I'll change colors here, 58.9 trillion. That's times 10 to the 12th. If you wonder how I get 10 to the 12th, write out a trillion. 1 trillion is, well, think 1. You just write out the zeros. See, this is a billion, and so there's a trillion. Count the zeros. You have 12 of them. So it is, this is equal to 10 to the 12th. 1 times 10 to the 12th. So if you have 58.9 trillion, this represents the approximate amount of money that exists in the world if it was all converted to dollars. And this number is much larger than that. So there doesn't even exist as much money as is on that checkerboard. It's pretty amazing. What I want you to see from this is when you have something like an expression like 2 to the n, this is called exponential growth. If you have something a to the n, as long as a is a number larger than 1, it means that the amount is getting big and getting big pretty darn fast. So you will use this same technique to do the problem of the paper folding, or as I said in my class, doubling the thickness of paper. So I hope this was helpful for you.